Okay, so now we're going to consider a second example of collisions in two dimensions. We already did a perfectly elastic collision, and so the other sort of common important special case is a perfectly inelastic collision. And that's where two objects come together like this, they collide, it's a hit and stick collision, so the two of them go off together with the same final velocity. So the final velocity of one object, v prime, is equal to the final velocity of the other object, big V prime. Okay, and so this is a classic Phys 121 example of a car collision. Okay, so let me just sort of like sketch the picture first. So what we've got is a car of, let's put it here. So we have a car of mass little m, which is moving down the road like this with some unknown speed v to the right. And we have a second car coming like this, and there's an intersection here where there's going to be a collision. Okay, so the second car is coming in with a mass big M. So this is a little sports car, say, and this is, say, an SUV or something, coming in with some other unknown speed, let's call it big V, and then there's a collision in the intersection. So one of these people maybe goes through a red light, and so there's a collision like this. Okay, and then when these two objects collide, we will imagine the situation is they they collide, all the metal gets crumpled up and so on, and the two of them are stuck together and they slide off in some direction. Okay, and so immediately after the collision, the two objects are stuck together and they're moving with some speed, v prime equal big V prime. So they're both moving with the same final speed, and they're moving together in a common direction, which we will call theta, some angle theta, like this. Okay, and so immediately after the collision, so I really should sort of emphasize this. So immediately after the collision, they have a common speed, little v prime equals big V prime. And then that clump of mass slides on the road. Now that road, so the tires are just skidding, sliding on the road, and so there's a coefficient of kinetic friction, mu k, and so then kinetic energy, whatever kinetic energy they had immediately after the collision, that kinetic energy will be converted into thermal energy, and they will come to rest, they will come together to rest. Let's just draw the crumpled mass of mass m plus big M, and suppose that they slide through a distance d before coming to rest. And there's a coefficient of kinetic friction between the tires and the road as this mass of two cars slides and comes to rest. So the final velocity of the m plus m system is at rest. Okay, so we got that. That's our basic situation. Now, the idea is, in the aftermath of this, what we see is these two crumpled cars at rest. And the question is, well, what were the speeds, the initial speeds, little v and big V, of those two vehicles? Because we want to figure out, was one of them, for instance, speeding? So there's a speed limit here. Of, say, 50 kilometers per hour. And so really what we want to figure out is, based upon the evidence after the crash, can we figure out the two initial speeds, little v and big V? Okay, so we've got that. So now let's think about this problem a little bit. So there are, as usual, especially in two-dimensional collisions, there are lots of sort of variables in the problem. So one of the variables is clearly the speed of the sports car, little v, the speed of the SUV, big V, that's a parameter that could be different. Another parameter is the final speeds of the two cars when they're clumped together, the hit and stick. So there is a v prime, little v prime equal big V prime. So we don't know what that is. And so we ask ourselves the question, none of those things are known here. So we ask ourselves the question, a police officer comes onto the scene, and what information could the police officer get about this situation? So, well, one thing that the police officer could measure is the angle theta, for instance, which they take off like this. So let's put that over here, theta. let's actually indicate that we're going to measure these things. So the police officer measures the angle theta. The police officer measures the distance that those two clumped together cars slid before coming to rest. And the police officer measures the coefficient of kinetic friction between the tires and the road. So those are things that the police officer can measure. And then the question is, given these measurements, can the police officer apply conservation of momentum and conservation of energy, which are always true, to figure out these two initial speeds? So that's really what we're trying to figure out here, is these two initial speeds. And so in particular, was one of these two speeding? Okay, so let's see. So our plan of attack is going to be the following. We're going to say we know that as this clumped together mass slides, we know that there is kinetic energy, the original kinetic energy that the clumped together two cars had immediately after the collision. All of that kinetic energy is going to go into thermal energy. So we should be able to use D and mu k to figure out how much thermal energy was generated. Where'd that thermal energy come from? Conservation of total energy tells us it came from kinetic energy. So then we can figure out the initial speed of the clumped together two cars at the initial point where they started sliding. Okay, so that's our first step, is we're going to, let's put these down here. So the first step is going to say we're going to use the measurements of D and mu k and conservation of total energy. Okay, so kinetic energy is converted into thermal energy. We're going to use that to tell us what the speeds of the clumped together two cars were immediately after the collision. So then we know this guy over here. Okay, and then the second thing is, now we're going to focus attention on what happened immediately before and after the collision. We're going to compare the total momentum before and the total momentum after. And so that's going to give us two equations. And together with knowing the angle theta, that we can then figure out these two initial speeds. So we're going to use the measured angle theta and conservation of total momentum. And that's going to tell us what these initial speeds, little v and big V, were. And then the third thing we're going to do, just out of interest, because whenever you analyze a problem in physics, you always want to sort of figure out everything there is possible to know about it, because some of these things are interesting. Okay, so what we're going to do is we're going to say, well, just before the collision, there was some kinetic energy in the system. Immediately after the collision, there was also some kinetic energy. The mass little m plus big N was moving with this speed little v prime equals big V prime. And so there's going to be some change in the kinetic energy. So we're going to use that the total energy, the fact that the total energy is conserved. So the total energy takes has two different parts, delta kinetic plus delta E other. Knowing little v and big V, okay, the speeds before, and the speed of the clumped together two cars afterwards is going to allow us to calculate delta K, and then we can figure out delta E other. We can figure out how much of the original kinetic energy in that system was converted into other forms of energy. For example, the sound of the collision, the thermal energy generated, the amount of deformation energy stored in the bent metal, all of that stuff. So we're going to figure that out. So this is a very rich and interesting problem. Okay, so I think we've got everything. What else? Oh, we're going to measure these guys. So let's give some data here. Let's give some numbers so that we can just start cranking it out. So let's suppose we have the following. Of course, the police officer, we always assume that the masses are known. The police officer can measure the masses of those two vehicles. So the police officer measures the following. He says, yes, the mass of the sports car was 1,500 kilograms. The mass of the SUV was more, 2,200 kilograms, let's say, and he measures. Run out of room. Let's put it over here. He measures the distance that they slide through before coming to rest under the force of kinetic friction. He measures that distance to be 8.4 meters. And what else were we measuring? The angle theta. Let's put mu k. So he measures mu k, the coefficient of kinetic friction, and that was 0.75. And the last thing he can measure is the angle theta, and he measures that to be, what did we say here, 40 degrees. Okay, so this information is then known. Police officer measures all of these things and then uses conservation of energy and momentum to figure out the initial speeds of those two vehicles. Okay, so our first step here is to use the idea that, yeah, there was some kinetic energy of the clumped together cars immediately after the collision that we don't know, but we know that all of that was converted into thermal energy. We can easily figure out how much thermal energy was generated, so we can figure out how much original kinetic energy was in the system. Okay, so we apply conservation of of energy here. So we say energy is always conserved. So there's no change in the total energy immediately after the collision and when the cars come to rest. And so what are the forms in which nature is storing energy in that slide? Well, there's obviously kinetic energy, and they started with lots of kinetic energy and then they had none. So there's going to be a change in the kinetic energy, which of course is going to be negative. And then there's a change in other forms of energy. And the other form of energy really here, the main thing is this is already after they have collided together. All the metal has been crumpled up, all the sound has gone out, all that stuff has already happened. And now we just have this crumpled together hunk of mass with some initial kinetic energy which just slides. And so the only other form of energy that we're talking about immediately after the collision and from that point in time to the point in time that they come to rest is just thermal energy. So there's been a change in thermal energy. There's a force of kinetic friction acting over that distance d, sliding, and so there's a generation of thermal energy. And that's, of course, going to be positive. So we can figure this out and then figure out delta kinetic and then hence determine the speed of that clumped together mass just after the collision. Okay, so let's do this. So that's change in the kinetic energy. So change in the kinetic energy, well, we have an object of mass big M plus little m, that's sliding here. So little m plus big M times the final speed squared is 0 minus the initial speed. The initial speed is this unknown little v prime or big V prime. Let's just put little v prime here. So that's the change in the kinetic energy as those clumped together cars slid. And then plus the change in the thermal energy. And the change in the thermal energy is always just, in the case of kinetic friction is of constant magnitude, and it always points up, it always opposes the motion. The motion is this way, the force of kinetic friction is this way. The work done, because the force of kinetic friction is constant, is just the constant magnitude of the force of kinetic friction times the distance that slid through minus sign, because that's the direction of the force, that's the direction of the displacement. So the work done by friction will be negative, and that's because thermal energy went up. Okay, so the change in the increase in the thermal energy is just the magnitude of the force of kinetic friction times the distance that the object slid through. And so the magnitude of the force of kinetic friction is mu k times the normal. So it's mu k times the normal. Well, the normal force that the road pushes up on the cars is obviously just the weight. So it's going to be little m plus big M times g. So little m plus big M times g. So that's mu k times the force times the distance. Okay, times the distance d that they slid through. Okay. There we go. Okay, so great. So the sum of these two things has to equal 0. So what's common to these two things is little m plus big M. So the mass is irrelevant. That cancels out. And so then we can solve for little v prime. So one equation, one unknown. And so we get that the final velocity, little v prime of the sports car is equal, so the final speed of the sports car is equal to the final speed of the SUV. And that's equal to the square root of twice mu k GD. Okay, great. Now the police officer has measured mu k and d, and so we plug in those two numbers, and what we get is 11.1 meters per second. Okay, so that is the speed of the clumped together cars immediately after the collision as they start their slide to rest. Great. So now we have figured out, what have we figured out? This thing over here. Okay, and so now what we want to do is figure out, well, what indeed are the two initial speeds of those two vehicles. So that's our second step now. So part B here is we're going to apply conservation of total momentum equal to 0. And this conservation of total momentum will be applied immediately before the collision and immediately after the collision. The total momentum must be the same. Now, of course, we can also apply conservation of momentum from immediately after the collision until they come to rest. And remember, this clumped together car definitely has some momentum in that direction. Okay, and then afterwards it has no momentum in that direction. Where did it go? Momentum is always conserved. Well, it went into the earth. Okay, because this clumped together mass of cars that's sliding this way is exerting a force on the earth in that direction. And that force acting over the time of the slide is going to transfer the initial momentum in that clumped together mass into the earth. Momentum is always conserved. Okay, but we're going to consider conservation of momentum immediately before and immediately after the collision. Okay, in which case none of the momentum has gone into the earth yet. Okay, and so in this case, we're going to just you look at the x and y components. Okay, so in this case, we'll take the x direction to be to the right and the y direction to be up like that. And so, because we have a car moving to the right, we have a car moving to up. Okay, and so that's obvious that we should do that. Okay, so we're going to apply the idea that the total momentum is of an isolated system, never changes. And so if we look at, so P total initial equals P total final, and we'll look first in the I hat direction. So what is the total momentum initially in the I hat direction? Well, the only thing moving in the I hat direction with momentum in the I hat direction is the sports car. And so it has a momentum that's plus little mv. Okay, momentum directed to the right along the I hat direction. And then afterwards, we have this clumped together mass, little m plus big M, moving with a speed little v prime equals big V prime, okay, in a known direction. And so there's some momentum, which is little m plus big M, okay, times the speed, little v prime equal big V prime. So that's the magnitude of the momentum. And then we need to determine the component of that quantity of motion in the I hat direction. So we just multiply by cosine of theta to get the projection onto the x-axis. Okay, so we look at that and we see that we can then solve for v. So little v, so the speed of the sports car just before the collision, is the sum of the masses divided by the mass of the sports car. Just take that down there, times little v prime times cosine of theta. Okay, so everything is known here. The police officer's measured the masses, he's measured the angle theta, and we just figured out, using conservation of energy, we figured out the speeds of this clumped together mass immediately after the collision is 11.1 meters per second. So we know that thing, and we plug in all those numbers, and what do we get? We get 21.0 meters per second. Great. And then we apply conservation of momentum in the j hat direction. And so initially, this has no momentum in the j hat direction, but the SUV has momentum in the j hat direction. Okay, so it's positive big M times big V is the momentum in the j hat direction of the SUV initially. And the total final momentum is we have an object of mass little m plus big M moving with a speed little v prime equal to big V prime. Okay, so that's the total momentum of the clumped together masses immediately after the collision, and we're interested in the y component of that, the j hat component, so the projection onto the vertical direction, and so that's going to be a sine theta. Okay, so again, everything is now known here, and so then we can solve for big V. So big V is the sum of the two masses divided by the mass of the SUV now, times V prime, same V prime, instead of sine theta, it's cos theta, it's now sine theta. Okay, sine theta. Okay, so everything is known on the right-hand side. You plug in the numbers and you find, what do you find? You find this is 12.0 meters per second. Okay, so that's great. So now the police officer has used his sleuthing skills to figure out the initial speeds of these two vehicles immediately before the collision. But now remember, the speed limit is 50 kilometers per hour. We have our answers in meters per second. So you just convert these things to, to kilometers per hour. And what do you get? You get 43.2 kilometers per hour for the SUV just before the collision. And you convert this guy turns out to be, what is it? 75.5 kilometers per hour. Uh-oh, busted. Okay, so speed limit 50. The sports car was moving at 75 kilometers per hour just before the collision. It's probably the one that went through the red light too. Okay, awesome. Okay, so that's good. So then the final thing that we can do with this problem, because remember, in physics, we're always trying to just figure out everything that is possible to know. And one thing that's interesting about any collision is, especially these hit and stick collisions, it's very easy to figure out because you know the initial velocities and hence initial kinetic energy. You know the final velocities and hence final kinetic energy. You can always look at the change in the kinetic energy. And that change in the kinetic energy is the energy that has gone into other forms of energy, bending, metal, thermal, and all that stuff. So we're going to apply conservation of total energy again, just immediately before the collision and immediately after the collision, before the slide has happened and kinetic energy has been converted into thermal energy. Okay, so now we're talking about the conversion of kinetic energy into other forms of energy like thermal and bending of metal and sound and everything else. Okay, so now we apply conservation of total energy again, immediately before and after the collision. And so that's equal to, well, there could be a change in the kinetic energy, and there could be a change in all kinds of other forms of energy. Okay, so these are generally positive here, and that's going to be negative. So there will be a decrease in the kinetic energy just before and after the collision. Okay, and so then we crank this out. So then we find that delta E other, well, that's equal to negative the change in the kinetic energy. So change in kinetic energy is final minus initial. Negative is the total kinetic energy initial minus the total kinetic energy final. Excuse me. So kinetic energy initial, how much kinetic energy was initially in, excuse me. It's, this spits up dust here. Okay, so initial kinetic energy, we have objects of mass little m and big M moving with speeds little v and big V. So initial is 1/2 little m little v squared plus 1/2 big M big V squared. We want to subtract the final kinetic energy. We have an object immediately after the collision. We have an object of mass little m plus big M moving with a speed little v prime. So minus 1/2 little m plus big M times little v prime squared. Okay, so then we can figure that out. And we know all of the velocities. And so this turns out to equal, I'll just stick it up here, delta E others, 261 kilojoules. Kilojoules, 1,000 joules. 261,000 joules. Okay, so that's an interesting number there. And the point here is, so what? Okay, so this much energy, this much of the original kinetic energy went into other forms of energy. So thermal and bent metal and all that stuff. But the question is this a lot of energy or a little bit of energy? So what you always want to do in physics problem is you want to compare your answer to some other meaningful energy in the system. Okay, and so in this case, well, it's the original kinetic energy in the system. So let's calculate the original kinetic energy in the system. So just this thing by itself. This is the original kinetic energy in the system. So we know those two velocities and those masses, so we crank that out, and that turns out to be 489 kilojoules. Not kilogram, kilojoules. Okay, great. So now this 261 kilojoules, we can give that some meaning. Okay, we can see what it really was really saying. So what it's saying is that delta E other divided by the original kinetic energy. What's that ratio? So that's delta E other, the amount of energy converted to other, the amount of kinetic energy converted to other forms of energy is 261 kilojoules, divided by the original kinetic energy in the system, is 489 kilojoules. Units cancel. We have a dimensionless ratio. And this dimensionless ratio turns out to be 0.53. So that's the meaningful number. So what it's saying is the original energy in the system, okay, which is just kinetic energy, plus rest mass energy and all this stuff. Those other things don't change. So the original kinetic energy in the system, and then some of that kinetic energy was converted to other forms of energy. How much? 53% of the original kinetic energy, about half. Okay, and then so we had some kinetic energy to begin with. About 53% of that energy went into bent metal and sound and thermal energy initially heating up. And then the remainder of that, so 47%, went into thermal energy during that slide. Okay, and so the road and the tires heated up. There was thermal energy went into that as these cars came to rest. And then you end up with no kinetic energy. All the kinetic energy has been converted into other forms of energy, first during the collision and then during the slide. Two separate sort of events that are happening. So that's really cool. This is a fun kind of a problem. It's nice and rich, and it's a great example of a perfectly inelastic collision, and it's a very standard physics 121 kind of problem. So there you go, perfectly inelastic collision example.